Hello, everyone. My name is Dane Banks, and for Biochemistry 3420, I am doing gluconeogenesis for our metabolic project. So to start off with, this slide is taken from Dr. Mackey's in-class slides. So overall, the gluconeogenesis takes a pyruvate and produces a glucose. So to start off with, you have pyruvate. From there, you use ATP, and as well as pyruvate carboxylase to turn into oxyl acetate. From here, GTP is used with PEP carboxykinase to produce phosphophenol pyruvate. From here, that is turned into 2-phosphoglycerate. From there, that is turned into 3-phosphoglycerate. From there, ATP is used to create 1,3-biphosphoglycerate, in which case NADH and some extra protons are used to peel off 2 phosphates to produce glyceraldehyde 3-phosphate. From there, it also produces dihydroxyacetone and phosphate, which those are interconverted between the two and eventually turn into fructose 1,6-biphosphate. From there, water is used to cleave off one of the phosphate groups, as well as fructose 1,6-biphosphatase 1 to produce fructose 6-phosphate. That is then converted into glucose 6-phosphate, and once more, water is used to cleave off another phosphate with glucose 6-phosphatase to produce glucose. So each and every one of those steps has many different functions, but we're just going to use the overall view. So now that we know what happens, gluconeogenesis is very much the inverse of glycolysis. When glycolysis uses ADP to produce ATP and 3-phosphoglycerate, 3-phosphoglycerate is then converted back using ATP into 1,3-biphosphoglycerate. So they have very much opposite cycles, which means they're interconnected in inhibitors and promoters. So anything that inhibits glycolysis will promote gluconeogenesis, whereas anything that inhibits gluconeogenesis will promote glycolysis. So what are things that will promote gluconeogenesis? Well, if you have a high ATP concentration, it will flow back into gluconeogenesis. It doesn't need the energy, and it will then store that energy as glucose. If you have a high NADH, that will also promote glucose, especially in the 1,3-biphosphoglycerate turning into glyceraldehyde 3-phosphate. That stage will be forced more forward, therefore more glucose. If you have low glucose levels, or if you're in the long fast state, that will also promote more glucose to be made and stored in order to survive more efficiently. If you have a high concentration of pyruvates, it will also push it towards glucose. So essentially, it's a scale. Anytime that glucose is pushed forward, gluconeogenesis is brought back. Anytime gluconeogenesis is pushed forward, glycolysis is brought back. So it's an interconnected system that is very delicate and requires many different factors in order to balance properly. So the real question is, what happens when that goes unchecked? What happens when gluconeogenesis has no inhibitors and is, or perhaps is fully promoted while glycolysis is unable to make up the dividend? So first off, just looking at an overview of what happens if gluconeogenesis is unchecked. It has no inhibitors. It goes fully through the reaction every single time it has pyruvate. Well, you're going to have a high glucose level overall, whether that is in the cell or if we're looking at a whole body perspective throughout the bloodstream and kidneys, everywhere is going to have a high glucose concentration. It also means you're going to have less ATP. If glycolysis can't go forward to create pyruvate, or such a limited amount is being able to be created and pushed through, ATP production is going to have to go through other methods than the glycolysis electron transport chain processes. It's going to have to go through fermentation. It's going to have to use less than ideal ATP production and therefore ATP is going to be generally lacking. You also have, since glucose is no longer being converted into ATP, you're going to have to break down fat and you're going to produce ketones, which, as we all know, is a very unsafe and ketone acidosis is a very dangerous condition. In several cases, this might cause cell death or organism death. This also has a very close relationship with diabetes. Although not fully the same, we're also going to discuss why they are very close. So what are some cases in which gluconeogenesis just occur? What happens when it goes unchecked? Well, you might have a cancer cell, for example. A cancer cell might inhibit glycolysis and promote gluconeogenesis in order to go through the fermentation in series. Cancer cell might also do other things along those lines, but that's one example. You might have an insulin-resistant cell to where the outer membrane of a cell is kicking out insulin or denying its access. Insulin is the primary inhibitor to gluconeogenesis as well. Insulin, we all know, is a very vital function. It's an enzyme that is thrown throughout our body. It's also technically a steroid. As it goes through, it inhibits gluconeogenesis and promotes glycolysis, breaking down glucose and producing ATP and pyruvate. So if you have an insulin-resistant cell, gluconeogenesis isn't going to be inhibited in that way. You also have diabetes, for example. We talked about several times before, but diabetes directly whether reduces the production of insulin or denies its access to the cell. You might also have a case to where your cell membrane, for whatever reason, is actually kicking out glucose into the blood or intermembrane spaces. If it kicks it out, all of a sudden there's a space of low glucose concentration, and gluconeogenesis will produce more glucose, in which case it's more kicked out. And so now it's a continuous feedback of glucose is made, then kicked out, therefore more glucose needs to be made. Glucose is made, then kicked out, etc. You might also have a case where the pancreas is destroyed, has suffered a significant injury, or otherwise, if you're stabbed in the pancreas, you're going to have insulin problems, or perhaps your pancreas is bursting, or there's a lot of various things that could cause the pancreas to stop functioning. If insulin isn't produced, gluconeogenesis is not going to be stopped. So you have a bunch of reasons as to why this might not occur. There's also some overall short-term effects and long-term effects, which we're going to go into. So overall, in a short term, whether it's hours, days, or weeks, you're going to be increased in tiredness, and you're going to be generally weak. You're not producing enough ATP to be properly equipped to handle day-to-day function. So you're going to be much weaker. You're going to get confused. Your brain isn't running on all cylinders. You're going to have an increased level of thirst. H2O is used twice in gluconeogenesis, so you're going to use a lot more water than you're used to for less ATP gain, so it's going to produce even more. You're going to get headaches, abdominal pain, and in some severe cases, you'll get a short-term coma from gluconeogenesis being unchecked. Now, if we look at the long-term problems with this, whether it is months, years, or decades, you might develop a cardiovascular disease. You might cause extra nerve damage. One of your kidneys might fail because of how much it has to filter the glucose out. You're going to have bone and joint problems. You might have poor blood flow, which might result in amputation. And lastly, open wounds have a greater chance of infection because of this. All of a sudden, your blood is a perfect environment for a bacteria to come in and fester. You have an increased glucose supply, which for bacteria, that's a perfect thriving ground, like to go into and infect. It's a life-promoting environment, and the chance of infection that you're going to take is greatly increased. So overall, this could easily lead to full organism death, or even almost certainly cell death due to lack of ATP production. As such, thank you for listening to my presentation. I look forward to hearing from peer reviews, and I hope everyone has a great set of presentations, and happy holidays.